The name of this video is Maxwell Inductance. Neumann. That is, we intend to use a Neumann integral to find the self-inductance of a loop. So, first off, do not get overwhelmed by the math in this series of videos I'm about to cover on the Maxwell inductance. They are complicated. The math is it's a lot. It's not very complicated, but it's a lot. Don't get overwhelmed, because if you get overwhelmed, you will miss the key points of all these videos, which are, first of all, I want to show you a way to make back-of-the-envelope calculations which allow you to find cool results in physics. Second, this series of videos will show you how to use series expansions multiple times nested into each other, which is something we do in science a lot. And last but not least, the way I managed to find the solution to this problem is by searching over and over references, because as it turns out, it's very hard to find the literature about this problem. And so if you want to recreate it yourself, you need to Google for many references until you find all the material required and all the math required to solve this problem. So these are the beautiful points of this problem. Do not get overwhelmed by the math, which is a lot, and I admit it. So let me give you the concept first that we are trying to do here. So the idea is something which at first glance seems super simple. We want to find the self-inductance of a simple loop that is a conducting wire with a certain radius. Let's call it radius capital A. And the wire is quasi-filiform, so there is a cross-section associated with it. So here, let me give you the idea of what we are about to do. And here there will be a major sketch, which we are then doing the math associated with that here. So the idea is as follows. This is our loop, conducting wire, characterized by a certain cross-sectional area. If the radius of this wire is capital R, this area will be pi capital R square. The radius of the entire loop, let's call it, as I already said, capital A. If R is much smaller than capital A, which in this case is not an area, is just the radius of this loop, then this object can be said to be quasi-filiform. I'm not going to write it down as a quasi-filiform wire, okay? What is the idea to use Neumann integrals to find the self-inductance of this object? Well, Neumann integrals are good for mutual inductances. So we are going to consider, instead of one loop, two loops. So the first loop is going to be the large one, which is going to have a radius capital A, and above it, there will be a smaller loop with radius small a. And the distance between these two loops is delta. So in other words, each of these two loops resides on a different plane. The bottom plane, this plane, there is one loop, and above it, there is another loop, a smaller one, on two different planes, okay? They are concentric, so the center of the first loop coincides with the center of the other loop when projected on these parallel planes, okay? The distance between the two planes is small delta. The radii of the two loops are capital A, larger than small a, respectively. Eventually, what we intend to do in this set of problems is to find the self-inductance by means of calculating the limit for capital A that goes to small a of the mutual inductance. In other words, first we find the mutual inductance between the small and large loop, which is function of capital A and small a. Then we go in the limit that the two radii are the same, and small delta. So these are the limits which we want to do. So under these limits, if delta is small, that's why I call it delta. So I have two different loops. Then I make them with the same radius, small delta. Effectively, they become the same loop. And so the mutual inductance emulates the self-inductance in the limit, okay? In particular, this limit on the a's, this allows us to remove the problem of divergence of Neumann integrals when you attempt brutal force naively to use them to find self-inductance, as we've seen in the previous video. Whereas the small delta, what this does, small delta mimics, emulates R, whereas this is to avoid, is for the Cauchy principal value, as I told you in the previous video. So delta emulates the fact that there is a radius, so we don't want exactly to go to 0, it has to be a small quantity, and it has to be comparable to capital R, because it emulates this radius, whereas the fact that capital A goes to small a is to avoid the divergence of the Neumann integrals, and therefore to eventually go into the Cauchy principal value kind of approach. So this is the concept, okay, that we want to show here. And so in order to do that, let me sketch these two loops, looking at them in two different projections, looking at this from above, and then looking at this from the side. Okay, so if I look at this from above, I need to sketch first the big circle here. So let's sketch it somewhere here. This is the big circle, it's centered here. And then we have the smaller circle like that. All right. So now here we want to consider a cylindrical coordinate system or a polar coordinate system in 2D, where this one is the r-axis. This is the var phi starting from 0 at this point right there. This is the origin of this coordinate system. Let's choose a few key points here. So first of all, we want to have a point on the outer circle here. Let's say a point here. This point, we call it capital P1, is on the first circle, which I will call gamma 1. I will put this at the end. Similarly, let's choose another point, let's say here, on the second circle, which eventually we will call P2. Capital P2 is this point here. This point up here, we will call it capital P3. Okay, so now the angle between 0 and capital P1, this angle, we call it var phi 1, whereas this angle from 0 to capital P2, we call it var phi 2. Okay? Therefore, this angle here, we call it phi, and this phi is nothing but the difference of var phi 2 minus var phi 1. Okay. So then let's look at the tangent unit vectors. So here, there will be a tangent unit vector in this way. So this is the tangent unit vector T1, which belongs to this line here. Here we have the tangent unit vector T2. And here we have a parallel line to that one, which intercepts this at point capital P4. This angle is 90 degrees, definition of tangent unit vector. Similarly, this angle is 90 degrees as well. This angle here, we call it phi tilde. This angle, so far unknown, we call it alpha. The sum of alpha and var phi tilde, of course, has to be pi. All right. Clearly, this one is parallel to T1, so it is T1 as well. And here, T2, we can also bring it here. This is a T2 if you want. So T1 dot T2 cross dot product is actually the cosine of alpha. That's why I show them in that location there. Okay, so the distance between these 2 points, P1 and P2, this distance here, we call it R tilde in 2D. The origin, we place it right there. So now we need to project all this onto the other plane, looking at it from the side. So this is the top view, the small circle, the bigger circle, the small, the big, looking at it from above. So I see them like this. Now from the side, I see the small delta, which is the gap between them. So I need to sketch all these set of 6 projection dash lines. Three, 4, then we want to have this one. And the last one would be this one here. All right. So these are 1, 2, 3, 4, 5, 6 projection lines. So now, if we want to sketch the 2 lines, so the big one goes from here to here. So this one is what we call eventually gamma 1, the big loop. The small one at the distance delta is this one between these 2 points. So it's this distance, is this line here, which we call gamma 2. So now I can put also the names here. This is gamma 1. This is gamma 2. The distance between these lines, this height, is small delta. In particular, the distance between this point here, which is this point, capital P2, and capital P1, which is this point, so P1 belongs to gamma 1, P2 to gamma 2, 1 and 2. This distance is what we call R, and this distance here is what we already called R tilde. So this forms a simple triangle with 90 degrees right there. Okay, so with this construction in mind, now we can proceed with the math associated with this problem. So the next thing we are going to do, we want to map this problem into find the mutual inductance between this loop and this loop. And so what do we use? We use a Neumann type of integral. So in order to find the Neumann integral, remember that there is mu naught over 4 pi, that's a constant, see from previous video. The line integral, the circulation along gamma 1, okay, in this case, dl1 gets mapped, if you look at this construction here, to what? What is dl1? Well, dl1 is a line element on gamma 1, so it has to be d var phi 1, which is an infinitesimal angle along this arc here, times the radius capital A, which is the radius of the big loop. So this is capital A, is this radius of the big loop, okay? This has to be integrated between 0 and 2 pi. So the circulation on gamma 1 of dl1 is just the integral from 0 to 2 pi d var phi 1 dA. Similarly, the circulation along gamma 2 of in dl2 gets mapped into the line integral from 0 to 2 pi of d var phi 2 small a, which is the radius of the small loop. Great. So now we have the first mapping done here. Now the next thing we need in Neumann integrals is the dot product T1 and T2. That's why, by no mistake, by no chance, I put T1 and T2, I report them close to each other, so you can clearly see what is the angle between them. Okay, they're all parallel, and so it's very simple to look at the angle like that. And so in this case, the angle, so T1 dot T2, which is in the numerator of Neumann integral, see the previous video for Neumann integral, this is nothing but the cosine is a unit vectors of alpha. Now, which is this angle here. Alpha, how do we compute it? Well, we know that this phi tilde and this phi belong to a quadrilateral, which has 90 degree here and 90 degree there. Therefore, simple algebra, simple geometry, phi tilde has to be equal to pi minus phi, from which it follows that, well, in addition, summing up this information, so using this information into the other information we have, which is the sum of phi tilde and alpha goes to pi, so phi tilde plus alpha clearly has to be equal to pi. Combining these two together gives us a result that alpha, which is what we intend to find because we need the cosine of alpha, is actually, if you do the math, exactly equal to phi, which we know is equal to bar phi 2 minus bar phi 1. Great, so we calculated this part here. What is the next thing we need? We need obviously this actual distance with these 2 points, and so we can do r tilde square plus delta square, okay? So this distance r is the square root of r tilde square, which is the 2-dimensional projection here. When I look at it from the side, this becomes r tilde. I know that people do mistake with that. Just look at it from the side and that's what r tilde is, plus delta square. So meditate a little bit about this r tilde square, but that's what it is, Pythagorean theorem. What about r tilde square itself? Well, now to find r tilde square, I need to look at this triangle here. This is r tilde, this is the distance, this is capital A, and this is small a, okay? Capital A, small a. So this is a triangle with an angle phi, so we can use the cosine theorem, which tells us that r tilde square is going to be equal to a square, capital A square, plus small a square, minus 2 times capital A, small a, times the cosine of the angle phi, which is actually nothing but bar phi 2 minus bar phi 1. And now we are basically done with all we need, because we can plug in this into here, and we get the denominator of Neumann integral, which is the distance between the 2 points. And so, finally, with that in mind, we can write the mutual inductance M21, which is equal to mu naught over 4 pi, the prefactors of Neumann integrals. The first circulation is the integral to 0 to 2 pi, and the second circulation is also the integral from 0 to 2 pi. So this one, we can put them here, d bar phi 1. This is d bar phi 2, as we have done up here. And then we need, in the numerator of Neumann integral, well, let's look at the denominator, which is the longer one. So it's the distance r, which is actually r tilde square, so a square plus a square, large and small respectively, minus 2 times aa cosine of bar phi 2 minus bar phi 1 plus delta square. That's cosine theorem plus Pythagorean theorem in one. This is denominator. T1 dot T2 is cosine of alpha, but it's actually nothing but, well, of course we need to remember also a and a, so it's aa times the cosine of alpha, which is bar phi 2 minus bar phi 1. So we have a beautiful integral just in bar phi 1 and bar phi 2. So let's circle this, which is worth doing. So this is the mutual inductance between these 2 loops, okay? Now remember that we want eventually to make this mutual inductance to become a self-inductance. This will come later on in the proof. The next thing we need to do, we need to face the reality of solving this integral. Does it look easy? To me, it doesn't look really easy at first glance. What is the integral of this stuff here? Cosine there? I don't know. Actually, as it turns out, I know, this is a fundamental integral in all electromagnetism. In particular, if one day you will study microwave engineering, you will find out that this kind of integral pops up everywhere. But actually not only that. So in my field of research, for sure in microengineering, this kind of integral comes all over the place. So it's this kind of structure, so you will recognize it. So it's really important that you learn this integral. Of course, Wolfram Alpha can do it for you, but this is something which, if you don't know what it boils down to, is very hard to do anything about. And so in microengineering, it comes up, in microwave engineering, it comes up all the time, in conformal mapping techniques, for example. Another place where it comes a lot in my research is in superconducting Josephson junctions, where eventually when you find the quantum mechanical equations of the junction, which is just tunneling between 2 electrodes separated by a barrier, by a capacitor, it's like a capacitor, but with tunneling, with quantum mechanical tunneling in it, the microscopic theory eventually leads to a number of elliptic integrals, which are exactly the solution of this type of integral here. So the solution to this is called elliptic integrals of the first and second kind. So first and second kind of elliptic integrals. This is such an important type of integration that you really need to know what it is, okay? Now, this is a full study of research and a full area of research, so we'll not go into the details to show you how this boils down to elliptic integrals, which would be several videos, which I don't want to do here. Instead, I will give you the final result. So if you know elliptic integrals, you will find out that this mutual inductance M21, in terms of elliptic integrals of the first and second kind, becomes minus mu naught square root of AA, capital A, small a, bracket k minus 2 over k times the elliptic integral of the second kind, f of k, plus 2 over k, the elliptic integral of the first kind, e of k. And the whole thing in brackets like that. All right, what is k? K is called the modulus of the elliptic integral, which happens to be equal by definition in this case. It's equal to, in the denominator, we have capital A square, capital A plus small a, quantity square, plus delta square. These are all the quantities we have in our sketch up here. And in the numerator, we have 2 times square root of AA. The larger radius times the smaller radius. This is called the modulus of the elliptic integral of first and second kind. So, to summarize this video, the idea is we want to find the inductance of a loop, of a wire which has the shape of a loop, a circle. It seems very innocent. As you can see here already, this is the first of a few videos. It is not that innocent. You can Google for it. Nobody tells you really how to calculate it. So I'm telling you how to calculate it. So how to calculate that is we emulate. First of all, we split this loop into 2 loops, one large and one small, one on top of each other on parallel planes with different radii, so that we can find the mutual inductance between these 2, which doesn't diverge because they are separated. Then we try to make them to have the same radius and a very small distance. The small distance is not 0 because it emulates the cross-sectional area of this wire, something which is due to Maxwell, actually, this contribution. And if you do that, this mutual inductance effectively becomes, in these limits, a self-inductance. The self-inductance of a loop, also called Maxwell inductance. Now, we sketch this in this projection from the top and from the side, which allows us to see all the angles and all the vectors and all the distances which we need in Neumann integrals. We perform up here the entire mapping of all the elements, all the bits and pieces you need in Neumann integrals to find M21, which is given here, okay? Particularly, be careful with all these angles, okay? You really need to be creative in making all these lines in such a way that T1 and T2 in particular are next to each other so you can clearly identify the angle very simply. Use Pythagorean theorem and cosine theorem to find this integral. This integral, when you find something of this shape, it is always elliptic integrals of first and second kind, and in this case, it boils down to this with this modulus. What are f and e? That's the beauty which is about to come in the next set of videos. We will investigate in the next video a series expansion, 2 series expansions, 2 different series expansions for f and e. One of them is the one you find on Wolfram Alpha or Wolfram S if you go now to Google for it. If you use that series expansion, you will never find a converging solution to this integral. So that fails. Instead, you need to dig into your references and go back and find a reference from 1912 of Alexander Russell, which is the only reference I found where is reported a Legendre series. Of course, Legendre publishes somewhere, I don't know where, but Russell gives it to us from 108 years ago. This Legendre series actually is a special series which, for our parameters, allows this to converge very quickly. So we can use the first order of that series, then do some Taylor series, and finally find inductance, which if you Google now, is given to you. That's it.